Ready? Okay, we have e-homework due tonight, and many of you have started it, as you wisely should, right? Because some of these take quite a long time, and you run into problems, right? Okay. So, up on the board, I have e-homework number 1, drawn, okay?
There's a pulley in here.
29, everyone's here, awesome. All right. In number 1, I believe that is the...
Thank you, Marcelo. I would totally put a monkey on a vine.
The link put itself on the vine.
Remember something to show a pulley.
All right.
It's like very
Is everybody okay with this? Look at what I've drawn. We have the penguin on the sled. There is friction between the sled and the snow. There is friction between the penguin and the sled. The sled is being pulled along. Okay? So we have one force on the sled right here. And the question is how big can that force be and the penguin not slide? Okay?
So basically we can ignore the snow, right?
We cannot ignore the snow because there's friction.
But then does that friction affect the penguin?
It affects the force.
It affects this force, right? Otherwise, your force that you'll get will be this much too small. Okay? All right, the deal is that they said the magic word. They said the magic word of not sliding, but maximum force so you just don't slide. So that means that our dreaded equation of less than or equal to mu force normal static, since we're at the maximum spot, then this becomes equal and it finally becomes of some use to us, right?
Yes.
We can actually use it in the equation. So, here's our equation for the or free body diagram for the penguin. Notice we have a normal force up, mg down, friction to the right, making the penguin move to the right. It's the only thing making the penguin move is friction. If there's no friction, then the penguin stays still as the sled goes out from underneath him, right? Or her. Okay. Now, since we're at the maximum, we can put the equal sign in, and these two must be equal, so that's our friction. Okay? Now, if we draw the sled, notice we have 6 forces. We have the force applied to the right. We have the weight of the sled down. We have the normal force up on the sled. We have the friction between the sled and the snow. But then we have these 2 forces that come from the penguin. The normal force down, which is the equal opposite pair of the normal force up on the penguin pushes down with the equal and opposite normal force back on the sled. Right there. Now, that should make sense because what should the normal force up be on the sled?
It should have to hold both of them.
It has to hold both. It should be m plus mg, right? Okay, but what we really get is the normal force is equal to mg of the sled plus the normal force from the penguin. But since the normal force of the penguin is equal to mg, it all comes out to be what we'd expect, right? M plus mg, right?
Yeah.
It all comes out. All right, this is the one that some of you might have missed right here. This friction force, static, maximum from the penguin. It's the equal and opposite force here. Now, we can figure out what this one is, knowing this information, plug it in here, knowing that, and the real normal force, and using the kinetic friction equation, we can find the maximum force, right?
So you have to take into account both of the friction forces on that one?
That's correct. That's correct. Because think about it for a second. If you tried to pull that sled forward without the penguin, it would be vastly different than with the penguin on top. And since the penguin is not physically attached to the sled, then the interaction of how that sled feels that penguin on there is through the normal force and friction. Okay? Now that's kind of an odd way to think about it at first, but that's what we do. In fact, if you go into things like sports medicine or whatever, they will do that. Like they will take a person, okay, and to figure out the stress in the person, like when they're running or jumping, like they have Olympic athletes. You know, they want to run as fast as they can, but if they're a distance runner, if their stride is too long, they put too much stress on their knees and ankles and things, and they can hurt themselves. So what they'll do is, in a simulation, they'll have a diagram of the person, the actual measurements of the person, and all that sort of thing, and they'll dissect the person on the screen. So they'll take their leg off, and they'll replace the leg right here with the forces, right here in the knees. They'll figure out what the forces are at the knee. And they'll do that for different stride lengths for that person. And then they'll advise the runner, okay, you could run a little bit faster if you lengthen your stride, by 2 centimeters or something. But if you lengthen it more than that, then you're just going to start putting too much pressure on your knee, and you're going to blow out your knee. So, they do crazy things like that. So what they do physically is just separate a part of it out, and then talk about the forces, equal and opposite pair forces, like that one matches that one, and this one matches this one. Does that make sense? And they'll just separate that out. Okay? They do that a lot for all kinds of things, like crash tests and stuff like that. They'll put crash test dummies in a car, and they'll crash the thing. And they'll figure out what the accelerations are in different parts of the body, and figure out what the forces are, figure out what kind of restraints they need to put in the vehicle so that they don't overstress parts of the body during a crash. All right, number 7. Number 7 looks like this. Okay, and we need to draw a couple of free body diagrams. So let's draw this top one here first. M1 looks easier to me. What is the question? What are they asking? Yeah.
Number 1, should the sled not be accelerating?
No, it doesn't give us. It doesn't give us the acceleration.
Huh.
So,
Because I've already, I just set F equal to both of the friction forces, and I already got it wrong.
Yeah, the sled is accelerating.
And how do we know how fast?
All right, up here, F equals ma. Right here, this is our force causing it to accelerate this way, right? So we end up with mu mg for the penguin equals the mass of the penguin times a. And the mass disappears, right? So we have mu g. This is the friction up top here, right? For the penguin. The static friction, right? Equals a. So we have that working for us, right? Up top. And then down below, in the same direction, F equals ma. We'll have F to the right minus this friction, which is mu mg penguin. And we'll have this friction, which is mu force normal,
so both ends.
but that normal, right? M plus m g equals m. Okay, which m do we have here in this diagram?
The one on the slide.
Just the sled. M, this is just for the sled, A. So this is the penguin and this is the sled. Okay? And so you can take this and plug it in here for A. Okay?
It's all bad.
You're still confused on 7 and 8, right?
Yes.
When I asked which ones you had trouble with, you said 1 and 7 and 8, right?
Yeah.
Okay. All right, here's number 7. And the condition here, it says you have a block on top, you got a block below, you got the bracket, you got the pulley. Pulley is magically frictionless and massless. And it says, what's the maximum force so that the blocks do not slide? Okay, now, wait a minute. Maximum force so the blocks do not slide. Ding, 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 ding. Magic words were said. We're at the maximum, which one? Maximum what?
Static friction.
Maximum static friction. So, we're going to use the maximum static friction right here. Force, friction, static, max, yay, we're happy, smiley face. Equals, not less than or equal, but equals mu force normal. Ta-da! So we can use that right there. Okay? Okay, so now let's look right here. Let's look at M1. So wait a minute. Since they're not sliding relative to each other,
Oh.
Is this approximate? Yes.
these two are going to move together, right?
Yeah.
But do you still have to?
No.
Yes.
Still.
But it's just like the penguin problem where you have to count the friction back.
Maybe.
Yeah.
All right, let's find out. Let's see if we can solve this the easy way first. I'm going to try and be sneaky. This may or may not work. And a lot of times when you start a problem, you got a great idea, it just doesn't get you where you want to go. Well, so let's find out. Since these two are going to be accelerating together, and which way will these two things accelerate? To the right. Okay? They're going to accelerate to the right because they're not going to slide relative to each other. So what I really have is this object all together with one force pulling it to the right.
Okay.
Right? Correct?
How is that going? How is it into? I thought the 10 kilogram
Because-
mass would go to the left.
There's no friction down here.
No, you're saying that they're not moving because of the friction or whatever?
Okay.
It's not
The
moving.
sum of the forces equals MA. How many forces do I have acting on this thing right here? What's the free body diagram look like? There's an M plus mg. There's a normal force. What else we got?
Force, you already got it labeled.
Ta-da! That's it. Because the friction and normal in here is an
Oh, okay.
internal force, right?
Because there's friction between M1 and M2, but not M2.
But
They pull it in all.
yeah, so like, like when you're running across the room and you want to figure out how fast you're going, your acceleration, you just want to know the force between you and the ground. You don't care about the forces like, inside your knees or neck or brain bouncing around. You don't care. That's all an internal force.
Thanks.
All right, so here we go. F equals M plus M A. Did that help us?
That makes more sense.
I mean, it helps, yeah, it helps.
No.
I don't
Because
know.
you're
Do we know what F is?
No.
Do we know what A is?
no.
Dang it. Okay, so this is a great idea that got us nowhere. Okay, now I'm going to put this off to the side.
No more than that.
F equals M plus MA. I'm going to put, oops, sorry, not some of the forces, but F. I'm going to put that over here in our little sidebar because maybe that's going to be of use to us later. We don't know.
There's like no.
Right now it didn't help. Okay, so we're going to have to split it up. Let's split it up.
There's two.
M1. How many forces on M1? 1, 2,
There's
One.
weight.
2, 3, 4.
There's weight. There's a normal.
There's a weight.
There's a force to the left.
There's a normal, I'm going to call it normal 1. There's a tension force to the left. You know what? This tension force to the left, what will it be?
F.
It's going to be equal to F. So I'm just going to write F. And what else we got? And we got a friction. Which way's friction?
Max static friction to the right.
F static,
Max.
no, F friction static max, which is mu force normal for us. Now, trick question. No, not trick question, just an intriguing question. Intriguing. All right, which one of those is bigger? F or the force of friction static?
Force of friction
Friction.
static.
Yes, why?
Because it's
It's
moving.
moving.
Because it's accelerating to the right. Now, if it was just moving to the right at a constant speed, those two would be equal, right? Or if it's stationary or moving at a constant speed, they'd be equal. But this one is bigger than that one because we're accelerating to the right. Very nice. So F equals MA. In this direction, positive. So I've got force friction static minus F equals M1A. Everybody okay with that? And then I'm going to plug in what static friction is. Mu force normal. Then I'm going to plug in what normal force is. What's the normal force in this particular case? M1G. So it's mu M1G minus F equals M1A. All right, can I do anything else with that?
You can
Or you know what F is.
Do I know what F is?
Yes, M plus
We have a
MA.
final thing for it if we.
Hey, hey! We know this, we know this, we know this, we know this. I have two unknowns, right?
Yes.
I know this and I know this, 1 and 2. And I have two unknowns. Ta-da, that did come in handy.
You're just
Plug in.
I think he's just.
Because now I have two equations and two unknowns. Now what most of you probably tried to do was to do this, and this is okay as well. You've got this little object here, and you drew the free body diagram for this one. Now, I'm going to draw it for this one anyway, although this is much harder. Okay, how many forces act on this thing? I predict 1, 2, 3, 4, 5. No, wait a minute. 1, 2,
Yeah.
3, 4, 5, 6.
What?
6.
No, that's crazy.
Label.
Weight of the thing.
Okay, M2G.
Normal from the mass.
Normal 2.
And normal from mass.
Okay, normal 1.
Max static friction to the left.
Okay, we got our static friction from that one. Force, friction, static, max. Sorry, this is getting a little small. And let me mark these.
And then
This one and this one are the same, and this one and this one are the same. Right? They're the equal and opposite pair. Okay, what else we got?
the force to the.
V force.
The acceleration.
I think that's
And who said it?
Who said it?
another force.
We have another force.
What?
Drag.
Why do we have two forces? Because it's a pulley, and the string is wrapped around. And so the string pulls twice.
It's directed to the right.
And they're both directed to the right.
But we don't have to do
You
that.
can't push on a string, remember?
The other way?
The strings only pull.
Mr. Bruin.
I push strings.
What does that mean?
Okay, look. If I take this object, here we go. Here's my string. Okay, and I pull this way,
Yes.
then if I were to cut it and recreate what the tensions were in it, the tension on this side would pull that way, and the tension on this side would pull that way. Okay? Huh? Here's my pulley. Here, hold my pulley. All right? And then if I pull right here, I'm actually pulling you twice. Okay? Does that make sense?
Wait, what?
Indeed.
Oh, I get it.
You get it?
Yeah,
I'm actually pulling him twice.
That's crazy.
I'm going to win. Okay?
So next time we play tug of war, wrap the string around the people, and then pull.
But the thing is, though, is actually I was pulling twice because I was attached to it twice, right?
Yeah, he had two arms.
If you want to win tug of war, then you hand them a pulley. You wrap it around. You pull on one end, but you put the other end like attached to a tree or a stake or something. Right?
I don't think that's valid in tug of war.
That's right.
That would not be smart if they.
Yeah, it's like we don't play tug of war. Here, hold this pulley.
Challenge to someone. Let me set it up first.
Wait a minute, this doesn't seem quite right. No, it's fine. It's the rules.
Have you ever played that tug of war?
We should do that. Play tug of war.
1, 2, 3, 4, 5, 6.
So, but we get to skip that, right? Let's do the other one.
That'd be awesome.
You ought to be able to get it with this one and that one. You just need two equations and two unknowns because you don't know F or A. Now, this one I'd like to write just because. All right, which way will this accelerate?
To the right.
Okay, so the sum of the forces equals MA in that direction. Here we go, everybody. We have F plus F minus force, friction, static, max equals M2A. This is M2. F plus F.
Okay, so, but they're equal,
But they're equal, so you could do 2F.
and they're really F.
And they're really F. You got it. All the notes. So you could have used this one. You can plug in what this is. This is mu M1G right here. And then you could have solved this equation and that equation, simultaneous equations, or you can solve any two of these. Pick any two of this one, or this one, and you should be able to get the same answer for the force and A. Actually, you're looking for F or A? You're looking for A, so substitute in for F to find A. Okay? Actually, I think in part 8 you got to find F anyway, right? So it doesn't matter.
Yeah.
Yes.
Okay, isn't F equals M plus M A, the A isn't it different from M1A?
No, because they're attached and not moving relative to each other. That's an excellent question. Everybody catch that?
I thought the acceleration on mass 1 was 0 since it's not moving.
Now it's 0 relative to mass 2, but they're both moving this way.
Oh,
Okay, everybody catch that? An excellent question. The question was, is this A the same as the A for this? And the answer is, it's because these two masses are not sliding relative to each other, they're both going to be moving that way. Okay? Even though this force is pulling this mass to the left, the friction is going to be bigger and they're all going to go off together, so they all have the same acceleration. Now, what would change if it slipped? Could we write this equation?
No.
No, this one goes away. That's not possible to write because they don't have the same acceleration. Okay, what changes here? This becomes kinetic friction, right? So you put in the kinetic friction number here. And this acceleration would be the acceleration of mass 1 only. Okay? And over here, this would be kinetic friction again. Kinetic. And this would be the acceleration of mass 2 only. They will have different accelerations if it was a slippage problem, if they were sliding past each other. Okay? I know in your review packet I've given you a slippage problem.
Ah, yes.
In fact, let's just do a slippage problem right now. I gave you the review packet, right?
Yes.
I gave it to you last time, right?
Yes.
Okay, I haven't put it.
Oh, I think that's.
Here's our next problem. All right, now if we really, really wanted to be mean, they can do this on the test. What they'll do is mu static 1, mu kinetic 1, mu static 2, mu kinetic 2. Okay?
You would never do that.
Sure we would.
Are you gonna be mean on your test?
Maybe. Listen. Shh. Now I could give you this problem where I would say, what's the maximum force where it won't slip? Right? And you could solve that because you could do this. No slippage would be this. You could put it all together, pull it to the right, and you could write F equals MA, and you would say, look, there is a M1 plus M2 G down. There is a normal force, there's a total normal force that way, and there would be one friction force this way. Would this friction force be static or kinetic?
So, it's not moving, right?
Okay, hang on, let me rephrase my statement. I'm giving a force here. The force will cause it to accelerate, but there's no slippage.
So it's friction.
Then this is going to slide to the right. The top one will not slide relative to the bottom one. Does that make sense?
So, but
Hang on a second, yeah.
So what is slippage where it just goes?
Slippage is here. Slippage is,
I know you showed it with the wheel the other day, but with the blocks.
here. Okay?
this one's not leaking.
This is no slippage. Okay? That's slippage. Okay? See the difference? All right, because in this one I have static friction between here and here. But here I have kinetic friction between the two. All right? That's the difference. Everybody catch that?
Yeah. This one's not leaking. It's like
Oh.
like
Okay, we'll keep continuing to
Kill
beat.
it.
All right, let's kill it.
it'll randomly go off.
All right, we'll throw it in the back room. Okay, everybody, that first free body diagram there on the board. Is for no slippage. If you have no slippage,
The blue one?
this one right here, yes. So no slippage. Then all we have here is kinetic friction here as the whole thing slides to the right.
Yes.
And you can attach the two together, and you can figure out what the acceleration is. Because you have F to the right minus force, friction, kinetic equals M1 plus M2A. Piece of cake, right?
Yes.
And then you could put in for kinetic friction, you can put mu force normal, but we know our force normal is
Large.
M1 plus M2 G. Nice. No slippage. Piece of cake. And if they want you to figure out the force between these two, like the friction force between these two, you just separate the one out, right?
Yeah.
And then replace the friction force that's there. Or show the friction force that's there. Okay, no slippage. No. Happy. Okay, now slippage. What if F is too big? All right, we have slippage. Okay, here's how we handle that. First thing to realize is that you can no longer keep the two objects together. This free body diagram here is of no use to us anymore. It's not valid. Okay? So what we have to do is we have to draw the two blocks separate because the two blocks will not have the same acceleration. In fact, which one has the greater acceleration? The bottom one, because it's directly connected to the force, so it'll have a force causing it to go to the right. The block on top will have a force causing it to go to the right, but it won't keep up with the bottom block, right? Correct, I mean? So here we go. Here's M1, and here's M2. Okay, what are all the forces on M1? What do we got?
Or what is normal?
We got an M1G, we got our normal number 1. What else?
Friction to the right.
Friction which way?
To the left.
Really?
Oh, wait, to the right.
To the right.
To the right.
Crazy.
Well, you didn't say up, that's good. Well, no, because a lot of times they'll say, well, it's to the left, but it's not to the left. It's moving to the right, so we naturally, instinctively think friction opposes the direction of motion, right? So our first guess is almost always, well, it's opposite to the way it's moving. But friction is opposite to the way it's sliding, and it's sliding backwards against the bottom one. Therefore, friction is forward, causing it to move forward. Okay? Force, friction, static or kinetic?
Kinetic.
Kinetic, yay, happy face, because kinetic we know is equal to mu to force normal.
Yes.
Okay, is that it?
Yes.
That's it for that one, right? Okay, how about the bottom one? What do we have?
Force to the right.
F. M2G. What else?
A normal force from.
Normal one down.
Okay, we got a normal from this one down, N1. That's the equal, oops, here it is, equal and opposite pair here. What else we got?
Normal two.
Normal 2 up from the ground on this one. I'm going to draw it down here because a lot of times that helps students realize where it's coming from. This one's from the ground up, this one's from the block above down. Okay? What else we got?
Friction.
We got friction this way, force, friction, static or kinetic?
Should be kinetic.
Kinetic, but that's from on block 2. Uh-oh, we better go up here and designate this one as on block 1, right?
Right.
Whoa, because we have two different frictions going on.
So you have
And there should
another
be
friction.
Another friction?
From
Ah, and there should be a friction pair from this one down here, right? And it's in the opposite direction. Force, friction, kinetic, 1.
on.
And this one equals this one.
Why is that one kinetic and that
Because they're slipping,
one? Okay.
right?
High slippage.
Yikes. You see the big difference between this year and last year? This year, we're splitting objects apart, and we have these equal and opposite pairs that appear, right? Okay. Next step would just be to write F equals MA. Now I want you to notice this normal here is equal to M1G again. So this one equals that one, which equals that one, which makes our normal force here equal what we'd expect it to be, right? This one's just going to be M1 plus M2G. So in the vertical direction, we've really solved pretty much everything we need to solve. Okay? But in the right-left direction, in the x direction, the sum of the forces equals MA for this one is going to be just force, friction, kinetic, 1 equals M1A1. Because we have a different acceleration for the top one than the bottom one this time. And this is going to be mu force normal, but our force normal is M1G equals M1A1. Our M1s go away, and we're left with mu G equals A1, and that's our acceleration for the top block. Oh, thank you. This is mu K1. Ugh. I think in your review packet I've given you one like this, where they have mu K1, mu S1, mu K2, mu S2.
So does that mean it's on the 10?
Maybe. All right. In the x direction for this one, the sum of the forces equals MA. What's this one look like?
F
F
minus F sub F K1 minus F sub F K2 equals M2.
There you go. Now, you see if you get your free body diagram drawn right, then you'll get this right, and then you'll substitute all the stuff in right. Yeah, maybe.
Yeah.
The answer is yes, yes, and yes. You
You
will.
make strange assumptions.
It's a pretty random assumption on my part.
Yes, very random.
Okay,
Very hopeful.
I am always hopeful. Hey, listen. All right, force, friction, kinetic 1. What do we put in here? That's mu K1 M1G. Now be careful, I jumped a step. This is normal force, right? If we're on an incline or something weird, then this won't be mg, right? Yeah, we cry more then. Or if we had something where we had a force like pushing down, then the normal force is not equal to mg. Just be careful. All right, this one is mu K2, and there's our normal force, M1 plus M2G equals M2A2. And there you go, piece of cake. That tells you what your acceleration is.
Very much.
Hey, and if the question is, what's the acceleration of block 2? Then all we do is just take this m and divide it here and we're done. Right?
Yes.
Sorry. Slippage. There you go. Slippage in all its wonder. And if you really want something weird, do a problem like this.
No.
Slippage on an incline.
Slippage on a slipping feet.
Yeah.
Okay, here you go. Here's a problem. You got coefficient of friction here, coefficient of friction here,
At an angle.
But they're both kinetic, right?
and you push this fast enough so this block moves up the incline. And then the question is how long does it take it to move from here to here? And how far does this one move? Ah!
Didn't we do it like that?
Yeah, then you could do a trajectory motion problem.
Yeah, you're gonna fall down.
Whoa.
You'd have to be moving though, right?
Don't give him any ideas,
Because if
then.
it's just like staying still, then it will be like.
No, it'll be moving because this one will start to accelerate that way and that way. So they'll have a net acceleration that way.
So we do it fast enough, it'll go this way.
That's right. So it will launch that in that direction. That's
That
correct.
makes sense.
I need my
like do a blunt force.
What we need is we need one of those tow trucks with the big flat bed, and you raise the bed up like this. You put ice. We need to put ice on it, and then we put you here, and then we have them back up really fast, and we can do this experiment.
I feel a little danger involved. Like crash into the ground before you
I sense lawsuit.
back up. Yes.
What I was thinking is that this like
I wonder why it's
that situation, at least the one we just did, isn't like tons useful for a long amount of time. It'll just fall out.
Hey, oh, excellent point. Everybody, what we just did here, how long is this stuff good for?
Ever.
Until the top block falls off the bottom block, right?
Oh, no.
Yeah, and this thing up there.
You know, so the question could be,
How does it land?
How far
the
does
question could be, that's a little harder. The question could be is, how far does the bottom block move before the top block falls off?
And that's a center.
And how do you
Now, you know what? That's not as hard as it sounds.
What about
Because all you have to do is figure out the relative acceleration between the two, which would be A2 minus A1, and that's going to be a constant. That's the acceleration relative between the two.
What was the question? How long? How far?
The question would be, how far does the bottom block move before the top block falls off? There are several ways to do this. Well, one way to do it would be to say, look, I'm going to figure out the relative acceleration between the two. When I figure out the relative acceleration between the two, you could do your kinematics equations again. Or you could do this. You could say, this one's going to move a distance x, this one's going to move a distance x1, this one's going to move a distance x2, and you could figure out these two with x equals x naught plus v naught t plus 1/2 at squared for each one, both of them starting at 0 and 0. And when the distance that this block travels and the distance that this block travels are exactly off by whatever this distance is, that's when it falls off. Does that make sense?
Okay, wait, what?
Here, everybody catch this? Look, another way to work it is this. You just found the acceleration right here and here for these two blocks. They both start at rest with 0 velocity, 0 position. You're going to yank the bottom one to the right. The top one is going to move a shorter distance than the bottom one. Whenever the distance that the top one travels is off from the second one by exactly this length, then it will fall off. Does that make sense?
Yep.
So
There you
is that
go.
saying, but
That's assuming
is
that.
that
Does that tell you about acceleration?
Yes.
Your equations kind of faulty.
It doesn't work?
no? Well, you have to change it a little bit because it gives us weight in newtons. So you have to take out.
Oh. Sorry, I didn't realize that. I just assumed that they gave you the mass. So since they gave you the weight of the penguin, you have to work backwards to find the mass, or, yeah, okay.
You could use this.
Other than that, is it okay?
Yeah.
Okay, good. Thank you.
I just didn't want people to.
Right, I didn't realize that. That's right, that's not my problem. Everybody, we have really about 4 different situations that we need to consider as far as drag, okay? We've talked about one already, and that's the issue of a person starts at rest and falls. Okay, if a person starts at rest and falls, okay, at time equals 0, we have mg only. And then at some time later, we have mg, oops. And everybody, it really makes a difference this time that you draw your arrows to the proper length, okay? Because on the test, a lot of times they'll ask you, they'll say, an object is falling in free fall under the influence of air resistance at some time t before it reaches terminal velocity. Draw the free body diagram. Okay, before it reaches terminal velocity, there's drag, but drag is less than mg, right? If you draw on the right leg. And then eventually we reach where we have mg and drag are equal. And that's when we reach terminal velocity. Okay? Now look, in each one of these cases, let's write F equals ma. F equals ma. In this case, it's going to be mg equals ma. And look, your initial acceleration is g. Right? Okay, now our next one is mg minus drag. Now, I'm just going to write bv to the n power. Okay? ma. The key thing here is a now is less than g. Right? Okay, next one. We have mg minus bv to the n power equals 0. Okay, everybody catch this? Very important. It equals 0. This is when we're at terminal velocity, and you can determine terminal velocity without calculus. It's just going to be mg divided by b to the square root of whatever that power is. Yes. Now, if this is just v to the 1 power, it's just going to be mg over b. If it's n is 2, then it's going to be mg over b to the square root. Okay? So you can determine the terminal velocity. You can determine the terminal velocity by just showing that these two are equal when you're at terminal. Okay? All right, now let's take a look at what the velocity and acceleration equations look like. All right, if we're going to draw velocity versus time and acceleration versus time for this situation, where do we begin for velocity?
0.
Where do we end?
Terminal velocity.
Now I'm calling down positive. We end up at terminal velocity. And we know that value. How do we get from one to the other?
You accelerate at 9.8 seconds squared.
Right here, you're going to have a slope of 9.8. But the slope will not continue to be 9.8. What will happen to the slope? It will get less and less and less, and so it's going to be asymptotic. It's going to look like that. And you will eventually reach terminal velocity. Does that make sense? You start off at 9.8 slope, but then it gets less and less and less as you go along.
Thank you.
All right, so what's my acceleration look like if we call down positive?
It's gonna be 9.8.
Starts at 9.8,
Asymptote to 0.
and it goes asymptotically to 0. And there you go. So this is going to have to be an E function. That's going to have to be an E function of some variety. It's an exponential rise to an asymptote or an exponential decay to an asymptote. Okay? There you go. All right, let's look at the opposite of this problem. What if the person is falling already? And they're falling at a velocity greater than, well, let's make it realistic. Let's say they're falling at terminal velocity. So I'm continuing this problem right here. So they're falling right here, mg and drag, and they're at terminal velocity. And then they pull their chute. Okay? When they pull their chute, what happens?
Their
Drag goes up.
Okay, their mg stays the same, but drag goes way up. And then what happens? They slow down because they accelerate up as they're falling down, which means they're slowing down.
Or up.
They're slowing down.
They're slowing up on their way down. Right. And so they will eventually reach a new terminal velocity, which will be much slower. Okay?
But at these,
You will eventually reach a new velocity where these are equal. But this terminal velocity with the parachute, will be less than the terminal velocity when we were in free fall.
So
Yes.
when the drag is greater than mg, then you have a positive acceleration.
That you'll have an acceleration up. Now, my problem over here is I called down positive to begin with, right? So let's redo these graphs, because that probably wasn't the smartest thing on my part. V and A. And this time we're going to call up positive. Okay, we're going to redraw this whole thing. Okay? So we're going to start at a velocity of 0, and we're going to fall. Okay? And we're going to reach terminal velocity. And we're going to fall, we're going to reach terminal velocity like that. Okay, it's just the opposite of that one. I've swapped them around. Okay? Okay, my acceleration is downward at 9.8. And then it goes to 0. Okay? So it's the same graph as before, I just swapped my sign. Okay, yes?
What is like n's name?
N,
Yeah, what is its name?
an exponent.
Will they give you most of the problem?
In x.
Yes, in the problem, I will tell you right now that in the AP problems, I've never seen it when it's not either 1 or 2.
so why is it different?
It depends on the fluid type and how fast you're going. When I was taking my aerospace engineering classes, we always used N was always 2 for air. But there are some fluid dynamic problems where N is 1. It depends on the viscosity and the density of the fluid. Now, there are possibilities where it might not be 1 or 2, it might be somewhere in between, but
It's never less than 1 then?
no, it's never less than 1 that I know of. I will open up myself to the unknown, I don't know. The only ones I've ever seen is 1 and 2. But could they put a 1.5 in there on the test? Sure. Just carry 1.5 around. Would they ask you to integrate that then? Probably. Probably not. Okay?
Wait. Would they ask you to integrate if it's a 1 or a 2?
They will ask you to integrate it all the way to the bitter end if it's 1. Because you
Well,
can
that's not
solve
ideal.
that. If it's a 2, I don't think it's solvable, if I remember correctly. It's not solvable with the calculus we know so far, anyway. Okay?
Okay.
All right, we're going to do one in a minute. Okay, look. When you pop the chute, chute pop time. Okay, what happens to our acceleration?
It goes down. Or negative.
Which way is our acceleration? Right here.
Acceleration goes
It's still
up.
Up.
positive, but I mean, it's decreasing.
The acceleration jumps to some value, and I don't know what that value is unless I go ahead and solve this equation, right?
We'll call it BVN minus M.
Yeah, we call it
Over
BV to the n minus mg
All over it.
all over m. That's correct. So it'll jump to some value up here. And what will happen to my velocity? My velocity down here is going to get a slope equal to this value of positive a. And then what's going to happen? You're going to slowly approach a new terminal velocity. Where will that new terminal velocity be?
Above.
Will it be this speed?
No.
You'll be falling at a slower speed, right? So this is velocity terminal with your parachute. And how will you approach that velocity? Like that, right? With a new exponential rise in this case. And your acceleration will jump up here and then go down like that. Because you'll eventually get to a constant velocity again.
So Mr. Maroon, that transition, it's smooth, right? But it seems pretty like radical. So
Well, it's actually not that bad. The chute comes out as a streamer first, and then comes out. It's not that bad. So this will not be an instantaneous jump. It'll actually come up like something like that.
Yeah,
in
that
the
would
real
probably
world.
hurt.
Yeah.
But other-
If it could instantaneously do that, then that would be really bad for you.
Break your spine.
And with your
Pull out your
net,
spine.
Probably
your
break a lot.
graphs, your 2 lines on the middle.
What's that? Oh.
If it went up really fast.
So, but for us, we'll assume it to be kind of like that.
He still doesn't connect.
The artistic you, isn't it? All right. Now, that's our first type of drag problem. Yes, sir. Here's another type of problem. Another type of problem looks like this. What if you have a vehicle, something like this, that's moving along with a velocity, and then it hits a resistive medium, like it starts to go through a big water puddle or something.
It starts raining.
Yeah, something. Okay? So it's going along and it hits something that offers drag. Okay, when it gets into the drag area, what are the forces on the vehicle?
Friction.
Drag.
Drag.
From where's the longer on which side?
Yeah.
Okay, yeah.
I think did I not give you this one in your review packet?
And then there is friction. There has to be extra friction.
Yeah, I know.
Oh, duh.
Yeah, I didn't. Actually, it looks kind of like it though. See, visualize this as car.
Okay.
All right.
It's the, what's that box car? It's the Honda Element box car.
All right. There's an mg, and there's a normal force. Okay, what's the acceleration of the vehicle going to be like? To the right is positive. That's the way it's going.
Okay.
So I have a negative drag force equals ma. Okay, what will the velocity and acceleration of the vehicle look like?
Velocity.
Okay, don't tell me, sketch it. What will the velocity and acceleration of the vehicle look like? So this is your initial velocity here, v naught, and then you go like this, right?
Yes.
Okay, what's your acceleration look like?
Just like that, flip it under.
Whoop.
Yeah.
Why is it negative? Because it's negative.
It's negative because it's.
And because slope here,
Does it start at negative?
this slope here equals this value, right? And then this slope here equals this value, and this slope here is 0, which is 0.
What does it start? What does the acceleration start?
Okay, what will your initial acceleration be? The acceleration will be negative fd over m. That value is that one right there.
Not too.
Okay, gotcha.
So unless numbers are given, it'll be a symbolic answer. Now, and in your review packet, I believe they tell you in your problem that this friction is equal to kV. So for yours, it would be A equals negative kV over m. That's your initial starting value. Okay?
So there.
But as your acceleration changes, so does your velocity.
Yes. Okay, now, do you start to see, can you see already that you can discover a lot about drag, but you can't tell, you can tell the initial values and the ending values, but not the mystery in between. Okay? So let's talk about the mystery in between.
Integrals.
Right above.
All right, here we go. Let's do the car problem first because it's actually a little easier.
Did anyone write that down?
Hey, I did.
Why did you
The acceleration equals
Because I can't write and listen to the next thing.
She can't read it.
All right, here's our car entering a resistive medium. In the direction that the car is going to the right. At time equals 0, it has a velocity. At time equals 0, v equals v naught. Okay? And it enters the resistive medium. We have only one force in that direction. It's negative kV in our case, equals ma. All right? Now, everybody, this is the key. This is our next big step.
Okay. Ready.
Look at the car, it says it right above it.
Yeah, but why is it?
Where do we go from here?
That's just what
It's
Calculus. A equals dv dt. Substitute it in. Negative kv equals m dv dt. Ooh, ah, that's so nice.
Yeah.
That's enough.
Now, everyone, this is called a differential equation. By the way, when you're solving this problem, I will tell you how they'll give you points. They'll most likely give you points for this, and then this knowledge and substitution. Setting up your differential equation may also be another point. And then from here, you have to, what do you do with the differential equation? Separate variables. Put the dv's and all the v stuff on one side, put all the t stuff on the other side. Okay? Now since I'm solving for v, I don't know, I'm going to put dt over here. I'm going to put m over negative kv dv over here. I don't know why, I just chose to.
Whoa. Because you can do it.
You sure can.
And now what do I do?
Integrate.
Integrate.
Yay, that becomes time.
Integrate from 0 to t and from 0 to v. My initial velocity, no. What's my initial velocity? V naught to v. And what's my initial time? So my initial time to any random time later. My initial velocity to any random velocity later. Now in math class they'd be mad at me for putting this variable here with the same variable here, but I don't care. Okay? So my left side of my equation becomes t.
M over negative k,
Alright, so this becomes m over k negative
ln.
v naught v dv over v.
Yeah.
Alright. By the way, putting the proper limits on is probably your next point.
Because I don't remember doing that little thing.
If you choose to do it with a constant and then plug your constant in later, your constant would be your initial velocity at time equals 0, your velocity is v naught, you'll end up with the same thing. So if you choose to do it that way, that's fine. In fact, I think if you, like during Saturday prep sessions and you go see Dr. Jensen and she shows you how to do drag, she likes to do it with coming up with a constant and then say, okay, what's my constant? When time's 0, what's v? And then she'll fill in what the constant is. And that's fine. That's the way she was taught. I was taught engineering-wise where we put our limits on. So that's the reason why I do it this way. If you like it the other way, that's fine. It doesn't matter. Okay, so I get t equals negative m over k. What's this integral?
ln of v minus v, or...
From v naught to v, right? I'm going to do it step by step.
Okay.
This is going to be what? ln of
V
v.
I mean, v minus
divided by...
technically.
Parentheses around.
So it'd be the ln of v over v.
Yeah, couldn't you?
And then you divide, right?
Oh, yeah.
Couldn't you do ln of v minus, or divided by v naught?
Yeah.
Because of a log?
Because this is the same thing as the log you can divide, right?
Yeah.
Okay. So t equals negative m over k ln v over v naught. I'm just doing every step because some of you will remember it and some of you won't. Yes?
Do you have to put it in the v over VO form, or can you leave it?
You will, and I'll show you why. Because we're not quite done. Because we want an equation for v equals.
So then you have to do the...
Yes. So look what I'm going to do now.
Yay.
Alright, now I move this to the other side. That becomes negative k over m times t equals ln v over v naught. I want to get rid of the natural log because I want to end up with v equals.
You got e to the...
So e to the negative k over mt equals v over v naught. So v equals v naught e to the negative k over mt.
That's cool.
So then to find the total, this is how we integrate that again.
Now,
That's so
Yay.
cool.
So lame.
If it doesn't have to be
It's cool.
Yay.
hey, now everybody,
I told you.
this is the exact curve that we sketched before. It tells you the value of the velocity at any time afterwards. Anytime at all. Sweet. Now, say it again.
What?
If I want to find x, then what do I do?
I want to meet the guy who came up with
Integrate.
Integrate it.
All right, I say, look, v equals dx dt, which equals v naught e to the negative k over mt. And so then I say, well, look, dx equals v naught e to the negative k over mt to the dt, and I integrate.
Hold on.
Yay.
We're solving for X, like the distance traveled.
You're funny.
I like
I'm gonna do that.
Now,
Wait, something's connected.
There's so many of those that are close.
It's like
yes.
yes.
Now look, there's a ton of constants in here.
There's one very important.
That's a constant, that's a constant, that's a constant. This is e to the x dx, which is equal to
From way over there.
e to the x divided by x, right? Or is it times x?
Times like the derivative. The derivative of the X.
What's that?
Yes.
But if this is e to
Times
the
x.
ax,
Then it's A e to the X.
then it's the d derivative of whatever ax was, right?
Yes.
Okay. So for us, this is going to be x from 0 to x, from 0 to t, because I start off at time 0 at location 0,
And you're afraid to press it, but
equals v naught
E to the minus. Just copy all
in
that.
the yeah.
right?
Maybe. Wait.
Okay, wait.
Oh, no.
Is that right?
Yes.
Wait.
Are we actually like where?
Yes.
Yes.
Counting to get if you're gonna be like this.
All right, hang on before you freak out.
Oh, you're a little bit late on that.
Hey, hey, hey! Before you get all freaked out, calm down. Okay, first of all, we got a harder one to do yet.
Oh my god. Isn't it M over K?
Is it m over k or k over m? Do you divide by the?
It's no.
It's m over k because when you do the derivative, it'll cancel out like the k and the m.
So it's m over k, right?
Math fails.
No, wait.
I was like,
What? No.
No,
No.
I'm not sure about it.
Because when you find derivative, you're gonna multiply by the negative k over m.
Yes.
And
Let's check the tome of wisdom.
k over m.
No.
What is that?
You're crazy.
This is the CRC
Or
math
I
handbook.
am. I mean, I think.
If you go into engineering, you will get one of these, and you will love it. Yes, you divide by it, so it's m over k. Because it's you divide by negative k
Yes,
over m, so it's
because if you
negative m
then
over
take the
k.
derivative of that, you would have to multiply by the exponent, making it 1.
Right. Very nice. Thank you. Very good. Yeah. So e to the ax.
No, wait. Don't you divide by...
This equals
You
that.
have to take an...
You divide by the derivative of the exponent. Right?
yes.
We're almost done.
Okay, hang on.
Okay.
You got to put in your limits. So that equals, what's this if it's 0? What's e to the 0 power? Oh, drat. So that means I get v naught negative m over k e to the negative k over mt minus 1. Right?
Yes.
But I have a negative, so it's plus 1.
No.
Yes.
Yes.
E to the 0 is 1, right? So that'd be.
This is 1. Oh!
It'd leave VO times n minus k.
VO m over k.
And it's subtracted.
So it's,
It's subtracted.
It's subtracted.
but I got a negative.
But it's a minus
So it's a
minus.
negative,
Minus
negative
minus.
plus the
So I get v naught m over k. 1 plus e to the negative k over mt.
That was a long time.
Right?
Sure.
You can't be talking.
All right, now, everyone,
Down and then when you
before you totally spaz out, how is this graded?
There's a grading?
Look,
This kid would take
Is it
a
wrong?
long time.
Yeah, it's fine.
negative.
1 minus
Ah.
b.
That's why I like to work better.
I was doing this test too.
I don't remember that.
I understand.
It was.
All right, now is it right?
Yes.
Okay, sorry, I had a plus. It's a minus.
Well, they're having very bad calculus.
Me, yeah, me calculus badly. All right, here we go. Yeah. You know I rely on all of you to do my calculus, right?
You know, none of us can do calculus.
That's the problem. Okay, here we go. Here's how it's graded. Setting up your F equals MA. Substituting in this. A equals dV dt. Setting up your differential equations. Setting up your limits. How many points do you get for this?
Nothing.
5,000 million.
Maybe one at the end.
Yeah.
Oh my gosh.
So set it up.
I deserve
If
like
you
6
run out of time, stop. In fact, all of you, when you set it up, stop. Go on to your other problems. Come back and solve your calculus problem later.
That is not gonna work.
Okay, when you get to here, how many points? 1 point. 1 point. Nothing, 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 nothing. 1 point.
Awesome, I won't do the last part. Wait, so
Okay.
there's gonna be a time where we're actually gonna have to like, yes.
Perhaps.
This sounds like.
The last AP test that we had after many years of almost no calculus on the exam, last year, the mechanics part of the exam, problem 1 and problem 2 both had calculus.
Is that what everyone said?
That's why everybody said they were mad, because there were 2 full-out calculus problems
Like
on it.
in-depth calculus?
Yes.
Not
like this.
Yes. Not this one in particular, but yes. Okay, now,
Is that the one that people did bad on?
okay, everybody, we need to solve really quickly, because we're running out of time, the free fall problem.
Yeah, up to the point where.
We're still on that one?
We've done that one twice. We've done that.
No, we haven't finished it. Okay, everybody, look. Sum of the forces equals MA, I'm calling down positive. MG minus FD equals MA. Hey, quiet.
No, don't call down.
Now, I believe if this is BV to the 1 power, I think you can solve it with calculus. If it's BV squared, I don't think it's possible for us to solve it with the knowledge that you have in calculus yet. Okay? So I'm going to try and solve it this way, and we'll see what we get. MG minus BV equals MA. Now, what's our next step?
A
Replace
is
the A with the ED.
Okay, so we get mg minus bv equals mdv dt. Okay, collect terms. Now I'm going to move dt to the left. I'm going to bring all my other junk to the right. So I'm left with m over mg minus bv dv.
Wow.
Now I think, well, let's leave it like that, okay? All right, now we have to integrate it. At time equals 0 to time t. At time equals 0, if you just fell off a cliff or something, what's your initial velocity?
T.
The sum. At time equals 0, your velocity would be 0 if you started from rest. Okay?
yes.
All right, now, here's where the dirty work comes in. That is not easily solvable. Your next step is,
Use of
Calculator.
okay, yeah, right. What's du then?
Negative b.
M and G are constant, so it'd be negative B.
Negative b dv.
So dv equals du over negative b, right? So I'm going to take this and substitute that in here. I'm going to take this and substitute that in here.
So m over negative b.
M over U.
T equals.
M over negative b is our constant.
So I get an m over negative b,
Oh.
integral from 0 to v. I have a
u over u.
du over u. Now look, I can solve that.
You want to change your limits?
I'm going to leave my limits and then resubstitute back in for you. That's just the way I learned it. If you want to change your limits, you can. Okay, so what does that become? t on the left equals negative m over b, natural log of u from 0 to v. Now I'm going to substitute back in what u is, because my limits on my u don't match up.
What you is.
What you is.
What u be. Whatever. U is mg minus bv from 0 to v.
In this case, you would need the absolute values on the ln
Yes, you would keep that.
because you have the minus in there.
Don't worry, it's not going to end up being negative.
So we don't really have to worry about that here, ever.
So what does this become?
The
When I
ln
plug in v, it's mg minus bv. When I plug in 0, what is it?
mg.
Right?
Yes.
Mg is always going to be bigger than bv, or at best equal. So it'll always be a natural log of a positive number or 0. So we're okay.
Okay.
Because it's
All right, now what do I do?
ln mg minus 0, right? You
What are we
plug
solving
in
for
your
then?
limits, right? You're gonna
Velocity.
Thank you.
Okay, we're trying to write an equation where v equals
and when you have subtraction
So,
of log
e
limits.
to the negative bt over m equals mg minus bv over mg. Now I just got to do math to get v.
Multiply by mg, then subtract. This. then subtract mg, and then multiply by a negative.
Got it, suckers.
Mr. Ryan, people are the third line where you just do divide by mg
Oh, he
is
did it
losing.
Okay, right here, this is ln of mg minus bv minus ln of mg. And then the minus is the same thing as divide in natural log, right?
Skip the stuff.
Since you're integrating and it's negative m over b.
No,
No.
he's leaving that out.
I think you need a negative b on your last one.
No,
Here?
you already-
No,
Click them.
I flipped the sides. I think I'm okay. Am I okay? I think that's my answer.
I have to go home and study them.
Okay, now, wait a minute. Let's check to see if my answer's right. We can check it. Shh, we can check.
No. No.
Look, quiet. We can check. This is my equation. When I reach terminal velocity, what's my acceleration?
0.
Okay? I reach terminal velocity when time goes towards infinity, right? When time goes to infinity, this is e to the negative infinity, which is what?
0.
So this all becomes 0. So my velocity terminal should be mg over b. Is it?
Yes.
Victory is mine.
Victory is
And I rest my case.
I think it's
So
ours.
basically what you just did is like, okay.
Okay, what I just did is check my answer, because at time equals 0, look what I get when I get time equals 0. I get e to the 1, which is what?
E.
Which is
0.
e to the negative 1. No, wait a minute. When time is
E to 0 is 1.
E to 0 is 1.
And then that's
e to the 0 is 1, so I get mg minus mg, and I get a velocity of 0. We start from rest, and we end at this,
Yay.
right?
Yay.
We check the limits. Yes.
Okay, the bt equals mg over b. Like that's the equation that was there. So all of this is like the derivation.
All of this is the derivation of what's in between the beginning and the end.
So that's what you were showing.
This is the actual equation of what the velocity is like in that curve. Does that make sense?
And that's how you, but that's all
That's the
this
equation for
long
B.
math.
That's the in
is how
between.
you
This is
do
the
that.
middle. The
Yes.
part that those mysterious.
He's proving it.
Yes.
Yeah.
So we're not gonna have to go through this for every problem.
All right, here. Okay, we got a valid question. Bianca's asking a valid question. The question is, do we have to do this every time? And the answer is, if they ask for it, you have to do it. If they don't ask for it, you don't have to do it. Most of the time they'll say, set up, but do not solve the differential equation. So where do we stop?
Like that.
There. Does that make sense, everybody? This is the differential equation. From here all the way to here is calculus. And they may or may not ask you to do that. But they will ask you what's the terminal velocity, which you can find without doing any calculus. They will ask you to sketch the curve, which you can sketch without doing calculus.
Because
They
it's
all look the
equals
same.
mg over b, like you don't need calculus.
To know the ending point, right. You don't need calculus to know the end. But you do need to know calculus to know this point, this point, this point, and this point. Does that make sense?
Yes.
Right. Okay, your